One of my friends requested me to explain KV cache to him, the concept of KV cache in a non-mathematical way. Right? So I kind of used this diagram to explain him the concept of KQV, the self-attention, and then how KV cache or where KV cache fits in. Right? So in this recording, I wanted to use the same diagram to explain the concept of KV cache, and then written a small Python program to show that when we use KV cache, how the latency of generating the token goes down. So, during inferencing, there are two stages, two main stages. One is the prefill stage, or the prefill processing stage, and the decoding stage. Prefill is when, when a particular prompt comes in the prefill stage, the KQV values for that prompt gets computed, right? And decoding is where this KQV values are used, and then the tokens are generated in a auto-regressive way. So the prefill part is somewhat compute intensive, and the decoding part is memory intensive, because you have to store the KQV values and the parameter values and all, right? So how does KQV, how do they work during the self-attention phase? Let's understand from this diagram, right? So let's say there is a prompt or a sequence of word came in, like the brown fox, like so. Let's say the first token or the first word is the, right? So how does the next word gets generated in an auto-regressive way, right? So first of all, what happens is each input word, so in this case, the is first tokenized. It's converted into numerical embeddings. Now, embeddings, think about embeddings as the numerical representation of the word, right? Now, every token embedding then passes through leverages three matrices. One is the WQ matrix, WK, and WV, right? Since we are not going into the mathematical part of it, think about that WQ, WK, WV are learned parameters during the training part of the language model, right? So when the language models are trained, this matrices, WQ, WK, WV matrices are learned as part of the training of the language models, right? So when so every token is then leverages this WQ KV to create the KQV matrix, right? So think about Q as so the Q value of a token is what it signifies is what that particular token is looking for in other tokens, right? K signifies what information that token offers to other tokens, and the V signifies if the token, if a particular token is chosen based on the self-attention, then how much or what content from that token should be carried forward, right? So to be more precise, or to explain it in a better way, Q, let's say for a token, if a token is a noun, right, then the query for that token, it may be looking for any other token that is a verb, right? So the Q value is telling others that, okay, I am a noun token, I'm looking for, are there any verb tokens, right? K is what information I as a token is offering to the others. Like if somebody, a verb, for example, if a verb token queries for who are the noun tokens, right? My K value, the token's K will say, oh, okay, I have the information, noun related information, right? And the V, as I mentioned, right, what part of that representation of that token should be considered for the context vector of that particular token, right? So once the KQV values are computed, so since here, let's say the is the first word, right? So we do not have anything prior to that. Here is self attention, it will attend to its same tokens. So the K value of the will be there will be matrix multiplication with the Q1. It's a dot product kind of like to find out like, okay, how the similarity between K and Q, right? Once that is captured, you multiplied, you basically do a weighted sum of the value vectors. So I'll multiply it by the value vector, and then I'll create the contextual representation of this token, right? Then it goes through the rest of the transformer architecture, the feed forward, like normalization and the final sigmoid, right, to get the next token, right? Now let's say I got the next token as brown, right? For this again, I will create the KQV values of brown, and I will now use the query vector or the query vector for brown and multiply it with the K value of all the previous tokens, including this token, to again like find out what type of, like, what similarities this have, like what type of like, are there any information that I can take from or how much I self attention I should give to the previous tokens and the token that is the token itself, right? So once again like this multiplication is done, it is multiplied by the value vector of the corresponding token to extract the weighted value, right? How much of that value I should consider in the context vector, right? So it will do K1, which is the key of the previous token, multiplied the query of this token, K2, which is its K2 value, multiply weighted summation with the value by multiplying the value vectors, and then you will create the context vector, right? Now it encodes the context, the entire context of whatever has come so far, right? Again, this goes through the feed forward network, and then the next token is predicted. And once the next token is predicted, again the same thing happens. For this token, now you create the KQV value, go through the same operation that I mentioned so far. Now here, if you see, if I do not maintain a KV cache, every time I am creating the next token, I'll have to recompute the K, Q and the V values for the past tokens also. But if I have a KV cache where whatever I have calculated before or the prior tokens, if I store in that KV cache, then I don't have to recompute that, right? I can reuse those values for the subsequent token. Only the next predicted token, only for that token, I need to compute the KQV values. For the others, I am just taking it from the cache, right? And that is the concept of KV cache in a very simplistic pattern. manner, right? And then when you hear about prompt caching in Claude model or OpenAI GPT models, that caching is this KQV caching, right? This key query value caching of these values, these metrics, the matrices, these are cached, right? So a lot of people think prompt caching is caching the prompt, right? But it is actually this KQV values, right? Now, let's take a look at a Python program, and that will help further cement this concept, and we can see how caching helps reduce the latency, right? So I took the GP2, I downloaded the GPT-2 model from Hugging Face. So if you go to Hugging Face, this is where the GPT-2 model is, and I downloaded some of these files to use it locally. So under models, you'll see I have downloaded config.json, generation config.json. These are the files I've downloaded from here, right? So that I can use this model locally. I didn't want to use one of the commercial models to reduce cost of running this program, right? So let's go through this program. So what I did is, so under models, I have the GPT-2 model parameters, right? I instantiated the tokenizer. This is what I'll use to tokenize the prompt, and the model is this model, right? Then in the generate token function, right, I so torch.no gradient, because I'm not training here, right? So I don't need gradient descent, right? So I don't need to track the gradients, because I'm using it as part of inferencing, not training, right? Then I am passing the inputs, and this input is my prompt, which is converted into, which has been tokenized. I'm passing that. We'll see these inputs down later on. Passing it to the model to get the outputs. Now the outputs give you, returns you the logits and the past KQV values, right? The key values, right? Which I was saying, like, those are the values that you put in the KV cache, right? So in the first run, what we'll do is we will not cache it. Basically, we'll not pass the past key values to the model inputs. We'll let the model regenerate these key values every time. So that we know, like, how it is actually, how KV caching is helping in reducing the latency, right? So I get the logits, right? And then the logits are nothing but the vocabulary space that it has, right? Based on that, it will have the score of each of the tokens in the vocabulary. And then I'm taking a argmax, right, which is the maximum score. That is my next token. I'm taking that next token and returning the next token and the past key values. Although I'm returning it, in the first experiment will not use it. The second experiment will use it, right? So this is my generate token logic. Now in the main, so I created a summarization type of use case so that we can see the difference in latency. The significant difference can be seen only when we have a lot of tokens involved in generation, right? So here I said, please create a summary of the below content. This is just a synthetic data that I have created, right, which describes the city of Metronia and all, right? But it's a content that we want to summarize, right? So first thing that I'm doing is I am tokenizing this prompt. I'm tokenizing this input, right? For the first time, right? This tokenization that goes as my input to the model, right? So I'm the next inputs, the inputs I'm putting into the next inputs, and then I'm looping the token generation for the first 100 next tokens, right? I could have also done, right, could have broken it after, let's say, US token or all, right? End of sentence token or something like that. But I looped it for next 100 tokens, and this is where I am tracking the time it takes to generate all the tokens, right? So this is where I am saying, okay, generate, I'm calling the generate token, which we already covered this logic, right? I'm passing the inputs, next inputs. Initially it is the after encoding embedding, this is what is going into the input, right? And then I'm calculating the time it took, and for the next iteration again adding it to the time. Later we'll sum up these times to see how much duration it took, right? Now next time we need to run, right, in the next iteration, see what I'm doing. I'm concatenating the the initial input IDs that I had, right, and the next token ID, right? Whatever I got here, right, that vector, I'm concatenating it, right? So whatever I had before, the next token I'm concatenating it, and I am also passing the attention mask here, right? So if you see here, I have not passed the calculated past key values. I have not added to this next input, right? So this is the first experiment that will run. Without that, we'll see how much time it takes, right? Then we'll try with this next input payload where we'll pass the past key values also, right? So now after I get the tokens, right, I decode it back, right, to get the actual word, right, and then since I'm running it for 100, right, those 100 tokens I'll concatenate it, and finally I'll generate the tokens, right? So let me run this and see what is the duration in seconds. Right, so it is running. Okay, let me push it up a little bit. Oops. Not okay. Okay, let me. I'm not sure why I'm not able to catch it. Oops. Very sensitive. Okay, it has now come up. So it completed generating the tokens, 100 tokens, and it took 20 seconds, right? And this is the summarization that it created, right? Now let me do the same thing. The only difference that we'll have this time is, last time I did not pass the key values, right? Now the past key values, which is the KQ calculations, the metrics, right, I'm passing that also in the next input, so that the inference engine does not have to recompute that. It should be able to get it from this cache like this. This is what I'm giving it as a pre-computed KQ values for the past tokens. So this is the only change where I'm passing the past key values. If I run this now, so earlier it was 20 seconds. Let's see now how much time it takes. Yeah, it took me 1 second. Earlier it took me 20 seconds. Right? So this is the beauty of KV cache. Now, what does that mean, right, for us when we architect LLM-based applications? This means that, like, we probably don't need to understand in details how the KV cache works underneath. Learning it definitely helps, but what we need to understand is that if we have to take advantage of the KV cache, our prompts need to be structured in a certain way. That means if we can have all the static part upfront and the dynamic part later, I would be able to utilize my KV cache in a more efficient way. If I have variable or placeholders in between the static, then it will have to again calculate the KQ values, right? So understanding how KV cache works, like the reason for understanding the KV cache is because it helps us to think about how we structure our prompts when we design our AI, Gen AI based application. Right? So that's all I wanted to show as part of this recording. Thank you.